Security Data Analytics and Visualization. Number 4, Machine Learning. Types of machine learning. Machine learning is an application of artificial intelligence, AI, that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. Machine learning focuses on the development of computer programs that can access data and use it to learn for themselves. We can essentially think of three components: an input, the data, a function, and an output. The machine is trying to learn the function that can map inputs to some form of output, which is achieved by minimizing some error measure, sometimes described as a maximizing a fitness function. One possible approach is to consider the difference between the expected output and the predicted output as an error measure. Supervised learning. Search optimization. Earlier, we introduced the concept of minimizing some error measure or error function. We can think about this as trying to find some minimum point on a curve. The challenge is that we do not know the minimum point ahead of time. Suppose we are at the red point on the curve, and we can look either one place left or one place right. By stepping along, we can find the minimum point on the curve. However, the curve in many challenges is not so simple. Here, we may then find many local minima, and so we may find a local minima that is not the overall global minima. This is why we attempt many different solutions in the hope of avoiding local minima so that we can find the global minima. Of course, in many applications, our curve may not be such a simple 2D curve. It may be a 3D surface or a much higher dimensional space beyond what we can visually convey. Methods of learning. Linear regression. Widely used in statistics, linear regression is an approach for modeling the relationship between a dependent variable and one or more explanatory or independent variable. This essentially gives a continuous value prediction of some outcome based on a set of numerical inputs. For example, imagine I want to predict house prices in my local area. If I know number of bedrooms and listed price, I can develop a mathematical model to express this, where number of bedrooms is the input and price is the output. For any number of bedrooms within my distribution, I can then predict the output price. Of course, the model may be wrong and would likely require more attributes, such as garden size, access to schooling, whether there is a driveway, and many other factors. We see here how multiple inputs variables will inform a single output value. I could model whether a network packet is malicious or benign in a similar fashion, where multiple inputs inform a single numerical output. The important thing to note here is that this will only model a linear relationship, i.e., there is a strong linear correlation between the inputs and the outputs, and so this is often too simplistic for many real-world challenges, but it does at least provide a useful starting point. Linear regression can be expressed in the form y equals mx plus c, where m is the gradient of a line and c is the y-intercept of the line. We can calculate the mean squared error, MSE, to measure how closely the data fits the line, where the smaller this value is, the closer the fit. Clustering. Here we want to observe when different observations form groupings of similar behaviour. Support vector machines. Similar to how we have described our clustering approach above, SVMs work through iterative search to find an optimal solution. Likewise, just as linear regression provides a line of best fit through the data, support vector machines aim to fit a line that provides a decision boundary so that data points can be classified. Specifically, we measure the Euclidean distances between data points nearest to the decision boundary. The objective is to maximize the distance between points and the decision boundary. The Euclidean distance essentially measures the distance as a diagonal distance. Think about the long side of a triangle and how you would calculate this distance using Pythagorean theorem. We can use the same formula as described earlier for linear regression, y equals mx plus c, to characterize the decision boundary line. Dimensionality reduction. Earlier, we commented that our search optimization may be in some higher dimensional space. We often use 2D or 3D visualizations to convey them simply because we cannot easily observe dimensionality higher than this. Yet, some dataset that has 100 different numerical attributes about each data instance could be considered to be a high dimensional dataset, 100 dimensional. Is there a meaningful way that we can visualize this data to identify data instances that may share similarities, or at least may make it easier to summarize the key characteristics of the data instance? Dimensionality reduction aims to achieve this, such that we can preserve the structure of the data in a low dimensional space that can be easily understood and visualized. Principal component analysis, PCA, is a widely used method of dimensionality reduction. For a given dataset, it essentially seeks to find the direction, or vector, of greatest variance through the data. Suppose we have some points in 2 dimensions. We can fit a line through this data, much like we have seen already. Then, we could treat this line as a new axis for our data, and essentially map our points against where they occur on this line. We could also imagine a similar approach if we wanted to map 3-dimensional points to 2 dimensions by finding a plane that all points could be mapped onto. Where we say plane, imagine this as a flat piece of paper being held at some orientation within our 3D points, and then placing a dot on our page where each point occurs. Other methods of dimensionality reduction include T-distributed stochastic neighbourhood embedding, TSNE, and uniform manifold and projection, UMAP. Dimensionality reduction is useful as part of unsupervised learning, where we want to cluster data but have no training labels to inform our process. Neural networks. Probably the most commonly described form of machine learning in use today is the neural network. The name derives from the notion of synapses in the brain firing when they receive a signal, where many signals contribute to whether a synapse should fire or not. Here, we have an input layer, red, which takes in some attributes about our data. For example, a set of numerical features that have been derived. For classification, the output layer would relate to the possible output classes of the data, where the highest scoring node would be the predicting class. In between are a set of hidden nodes that the machine will attempt to learn a suitable numerical value for, such that input nodes map to the expected output nodes. We do this using matrix multiplication. We will show this further in the practical sessions. The important detail to know is that neural networks are calculated as y equals sigmoid in brackets wx plus b, where x is my input vector, for example, 5 numerical values in a 5 by 1 column. W is a weights matrix, where the matrix has the same number of columns as the number of rows in our input vector, and B is our bias vector that is added as a constant. The sigmoid function then scales our resulting vector so that our value remains within our set bounds, either -1 and +1 or 0 and 1. What we have described is often considered as a feed-forward network. Since our model is likely to incorrectly predict our data initially, we need a method for updating the weight values in our hidden nodes, since these essentially dictate how our input relates to our output. This is done using a technique called backpropagation. This essentially works like the search optimization technique described earlier, where we seek to minimize the distance between the predicted values and our expected values, which is achieved through the process of training the neural network. For our purpose here, we want to understand what different techniques exist for machine learning. Here, we are not going to focus too much on the underlying mathematics used, although it is important to understand how these methods operate and why. Neural networks have formed the basis of much modern machine learning research. The concept of deep learning comes from having many hidden node layers in a neural network structure, such that it is a deep neural network. Furthermore, there now exists a wealth of different architectures based upon the notion of deep learning. Convolutional neural networks have become particularly popular for image analysis tasks. This is because instead of having single vector inputs, they use square regions as input, which means they are much better at preserving spatial attributes, such as the relationship between pixels in an image. The final method to mention here is recurrent neural networks, which are designed to work on sequential forms of data. Whereas our previous learning models have treated each data instance as a discrete observation, in a recurrent model, each instance of data is dependent on what came before. A common example is language modelling. So similar to subsequence anomalies discussed in section 3, our model could learn that the input phrase, "the quick brown fox jumps over the lazy," is completed by the word dog. We have covered a lot of ground in this section, but hopefully this helps to give you a brief introduction to the different machine learning models that are used. In particular, we have seen how each model takes an input, performs some processing or operation, and provides an output. We have also seen how this is based on minimizing or maximizing some function over time through the process of training to achieve the final output. It is important to think about the task to be solved as to which method is most appropriate. Are we hoping to predict a class, classification, a continuous value, regression, a group, clustering, or some complex nonlinear function that is harder to imagine. Neural networks. As a slight aside, when using machine learning for the purpose of cybersecurity, it is vital that we consider the case when an adversary is able to manipulate the performance of our model. You may have seen examples of this, where image recognition systems can be made to misclassify objects, despite having a well-trained model to use. Think about the impact here for up-and-coming domains such as autonomous vehicles and healthcare. This is why, when we think of AI for cybersecurity, it is fundamental that we also think about cybersecurity of AI. We are merely scratching the surface here. However, there is much research activity in the area of adversarial learning. In the practical guides for this section, we will cover how to implement clustering, linear regression, and neural networks using Python and the Jupyter Notebook environment.